We now take up for discussion an equation which is known as the Bernoulli's equation, and that has a very standard form, dy dx plus py. On the right hand side, instead of just q, we now have py and qy to the power of n, where n is of course not equal to 0. Now, by a simple substitution, this equation can be converted to a linear first order equation. So, we will see how to get about doing that. What we do is, we divide the entire equation through by y to the power of n. So, if we write dividing y to the power of n, actually the best way is to write dividing through. That gives the message that we have to divide the entire equation, the right hand side and left hand side, by y to the power of n. We will get y to the power of minus n into dy dx plus p y to the power of 1 minus n is equal to q. As we mentioned earlier, p is a function of x, q is a function of x, and y is the dependent variable and x is the independent variable. Now, we make a simple substitution. If we write z for y to the power of 1 minus n, so we say let z be equal to y to the power of 1 minus n. Then we have dz dx as y to the power of 1 minus n minus 1 dy dx. This is by the chain rule. So, dz dx is 1 minus n times, there is of course 1 minus n factor here, 1 minus n times y to the power of 1 minus n minus 1 dy dx. In other words, this is y to the power of minus n. So, we just drop out a little bit on top and take this expression up. So, we get from here one minus n times y to the power of minus n dy dx is nothing but dz dx. There we are. In other words, y to the power of minus n dy dx, that means this term, so that becomes simply y to the power of minus n dy dx is 1 over 1 minus n dz dx. So, the equation now can be written further simplified as dz dx divided by 1 minus n plus p z is equal to q. So, from taking our strength from here, we can modify this equation, but before that let me rub out this part. We can modify the equation to 1 over 1 minus n dz dx plus p, this is z, is equal to q. In other words, this implies that dz dx plus p into 1 minus n times z is equal to q into 1 minus n. So now this is a linear first order equation involving z as the dependent variable and x as the independent variable, but there is no loss of flavor from what we have done in terms of y and x. Evidently, if we see this equation on a standalone basis, and if we recall what we have done earlier, then the integrating factor for this particular equation is, let's say, integrating factor is e to the power of integral p 1 minus n dx, integrate with respect to x. That's it. Once we do this, the equation can be solved by whatever methods we have been doing so far. We now take an example of another example of Bernoulli's equation to drive home the thoughts that we have discussed so far. Now, if we simplify this, we will get the following equation. If we transpose this on the right, then one step is this, transposing the left hand side term on the other side, and then we can write dy dx is equal to, take this here, cross multiply y times 2xy plus e to the power of x divided by e to the power of x. Dy dx is equal to y into 2xy plus e to the power of x divided by e to the power of x. In other words, this is nothing but 2xy square e to the power of minus x plus y. The algebra is correct, hopefully. In other words, we take the y on this side and let's see what we get. We get dy dx minus y is equal to 2x e to the power of minus x into y square. Now one can see that our p is minus 1, dy dx minus p, this is minus 1, and of course q is this much. So p is minus 1 and this is the expression for q. So that's really not necessary, because the first step we do is to divide the entire equation by y square and try and see how we can transform this equation into a linear first order equation. So we rub what is appearing on top and retain this equation. And of course, for convenience, we start with this equation a little on top so as to work below. So we have dy dx minus y is equal to 2x e to the power of minus x into y square. We divide by y square the entire equation. If we divide by y square, we will get y to the power of minus 2 dy dx minus y to the power of minus 1 is equal to 2x e to the power of minus x. That is dividing the entire equation by y to the power of 2, y square. Now, we will substitute z for y to the power of minus 1. So, if we do that, we write let z is y to the power of minus 1, which implies dz dx is minus y minus 2 dy dx. In other words, y to the power of minus 2 dy dx, which is this term, is nothing but minus dz dx. We'll make that substitution and write from here we get minus dz dx minus z is 2x e to the power of minus x. If we substitute, or rather if we replace every minus term with a plus, then we'll get plus z is equal to minus of 2x e to the power of minus x. Now here we have a simple equation in z and x. Z is the dependent variable, x is the independent variable, and the integrating factor is e to the power of 1 dx. So IF is nothing but e to the power of integral 1 dx, and that is nothing but e to the power of x, e to the power of x. When we multiply the entire equation by e to the power of x, we will get e to the power of x dz dx plus z into e to the power of x is minus of 2x, because e to the power of x and e to the minus x annihilate each other. So on the left hand side we have the d dx of z times e to the power of x. So if we put an asterisk here and climb a little higher, we get on the left hand side this is d dx of z into e to the power of x, and that is nothing but minus 2x. If we just carry out one integration, this implies that z e to the power of x is is minus x squared plus c. We must remember that z was nothing but y to the power of minus 1. So this implies y to the power of minus 1 e to the power of x is equal to minus x squared plus c. If we recognize that this is 1 over y and k to multiply by y throughout, we will get, this implies e to the power of x is y x squared with a minus sign minus cy. This is the solution of the equation we started out with, because it gives an explicit relationship between y and x, and of course it is the general solution because the number of arbitrary constants involved in the solution is 1, which is equal to the order of the equation. It is linear and the first order equation, so this is the general solution. One can express y explicitly in x, in terms of x, but that's not necessary. It's easy in this case. We now take an equation which is an example of Bernoulli's equation, but this is not in a very straight, recognizable form of Bernoulli's equation, because actually I would say it is a Bernoulli's equation in disguise. But nevertheless, we'll try to see how to handle this. First of all, we will divide by cos square y, both sides. So dividing through by cos square y, we will get 1 over cos square y dy dx, that is sec square y dy dx. Plus 1 by x sine 2y over cos square y is equal to x cubed into 1, of course. Now we need to simplify this sine 2y over cos square y. If one remembers that sine of 2y is 2 sine y cos y, then 1 by x, 2 sine y cos y, 1 cos y will get annihilated and we will be left with 2 tan y. So this tells us that sec square y dy dx plus 1 by x, or rather 2 by x tan y is x cubed. Now this is a more manageable form. Supposing we put tan y as z. If we write, let us say z as tan y, then we immediately have dz dx as sec square y dy dx. So things seem to fall in place very fast. The sec square y dy dx term is nothing but dz dx. So this implies that after the substitution, we have dz dx plus 2 over x into z is equal to x cube. No change on that term. Now here the integrating factor is e to the power of 2 by x, integral 2 by x. So we will rub out a bit of the work done so far to get a little space. E to the power of integral 2 by x dx, that is e to the power of 2 log b base e x, and that is nothing but x to the power of 2. So if we do that, we will get x to the power of 2 multiplying by the integrating factor here, x to the power of 2 dz dx plus 2x into z is equal to x to the power of 5. In other words, the left hand side, which is easily recognizable to be the d dx of x square times z. And this implies, upon integration, that zx squared is the integral of x to the power of 5 with respect to x, and that is equal to z to the power of 6, x to the power of 6 by 6 plus constant. Now we had put z for, well, I forget it's rubbed out, but z was in terms of x cos square y. Whatever z was, z to be replaced by y terms. Its equivalent y term. So that would be the solution.